Read the given problem carefully. It is advantageous to draw vectors on the coordinate plane with the origin as the reference for interpreting the problem. The wind is blowing at a speed of 60 miles per hour in the direction 60 degrees east of north. The airplane is flying at a speed of 500 miles per hour in a direction slightly tilted south from east. The reason for flying slightly downward is to head east while considering the influence of the wind. We have already learned in past classes that the sum of the vectors for wind speed and airplane speed forms a parallelogram's diagonal direction. Since the actual direction of the airplane is east, the y-component of the sum of the two vectors should be 0. The velocity vector of the airplane is as follows. Let's call any angle theta. The velocity vector of the wind is as follows. The direction angle is 30 degrees, not 60. The sum vector of the two velocities is as follows. As the y-component should be 0. When we solve the equation, using the inverse sine function, gives the value for theta as negative 3.44 degrees. The actual velocity vector of the airplane is calculated by substituting negative 3.44 degrees for theta. The actual velocity vector is x component 551.061, y component 0. Therefore, the actual speed of the airplane is the square root of the sum of the squares of the two components, which is 551.061 miles per hour. Of course, since the y component is 0, you can intuitively calculate it as well. Moreover, the initial angle, bearing angle, needed for setting the direction of the airplane is 93.44 degrees. This can be expressed as negative 3.44 degrees in direction angle, or as 3.44 degrees south of east. Here is the second problem. The boat is moving at a speed of 30 feet per second, heading 15 degrees above the east horizontal line, while the river flows south at a speed of 5 feet per second. Representing the boat's velocity as a vector, we have as for the river's flow represented as a velocity vector, it is 0 and negative 5. This is because the direction angle of the river is 270 degrees. The sum vector of the two velocity vectors is so. The actual speed, magnitude, of the boat is 29.110 feet per second. The actual direction of travel is calculated using the arctangent of the y-component to the x-component of the sum vector, approximately 5.451 degrees. Due to the influence of the river, the boat actually moves about 5.451 degrees above that. The actual distance traveled by the boat, represented by the red straight line, can be calculated using the cosine value of 5.451 degrees. Therefore, the actual distance covered by the boat is approximately 1004.543 feet. Now, how can we calculate the time it takes for the boat to reach the opposite side of the river? Since distance is the product of speed and time, the travel time is approximately 34.5 seconds. See you next time.